lecture in Cambrian geologic history in this lecture to build a knowledge base of how tectonics affected early Paleozoic biological evolution. As you can see on the geologic timescale, we are now in the Phanerozoic eon, which represents only 12% of the 4.6 billion years of Earth history. The Phanerozoic eon is further divided into three eras: the Paleozoic or ancient life, the Mesozoic or middle life, and the Cenozoic or recent life. We live in the Cenozoic era. In this lecture, we will focus on the Cambrian and Ordovician periods, ending with the first of the Big Five mass extinctions at the end of the Ordovician period. We need to understand some of the basic rules in terms of geology as we go forward. A transgression is a rise in sea level, while a regression is a drop in sea level. Convergence leads to mountain building, called orogeny, and orogeny leads to weathering and erosion as mountain chains are forced upward and exposed to elements. Transgressions and regressions are caused by one of two things: either glaciation events or tectonic activity. This illustration is a basic diagram showing an oceanic continental convergent boundary with a volcanic arc, mountain range, forming. Continental-continental convergence is responsible for forming most of Earth's greatest mountain ranges. As mountain ranges rise, they expose sediment to weathering, and this leads to erosion of continental rocks. We also need to understand the architecture of the continents. A craton is the stable, immobile part of the continent. In this illustration to the right, the dark brown part of the diagram is the North American craton, called the Canadian Shield. Mobile belts are located along continental margins. They receive sediments and deform during continental collisions. In other words, they are areas where mountain building occurs. In this illustration, there are four mobile belts on the North American continent: the Appalachian in the east, Cordilleran in the west, Franklin in the north, and the Ouachita in the south. One other term we need to know is the term epeiric seas. Epeiric seas are widespread, shallow seas that transgress and regress over the continents through time. This illustration is a map of the placement and orientation of the North American continent during the Middle Cambrian. Notice the position of the continent over the equator highlighted in yellow. What can we infer about the climate at this time from this map? The Cambrian world consisted of 6 major continents at low tropical latitudes. Water circulated freely among ocean basins, and the polar regions were mostly ice-free. The continents being widespread allowed oceanic circulation between continents, which has a moderating effect on the climate. In addition, most of the continents were located at low tropical latitudes, so there was a fairly uniform and warm global climate. This is the paleogeography of the continents during the late Cambrian period. Notice that unlike today, where most of our land masses are in the northern hemisphere, many of the land masses at this time were at tropical latitudes and in the southern hemisphere. The Paleozoic history of most continents consists of major mountain building activity along margins and numerous shallow water marine transgressions and regressions caused by global changes in sea level that are related to plate tectonic activity and glaciation. The geologic history of the North American craton may be divided into two parts: a relatively stable continental interior over which epeiric seas transgressed and regressed, and mobile belts where mountain building occurred. The sedimentary rock record of North America is subdivided into 6 cratonic sequences. So, what is a cratonic sequence? It is a large-scale lithostratigraphic unit that represents a major transgressive-regressive cycle and is bounded by unconformities, a period of no deposition when rock is eroded. There are a total of 6 cratonic sequences extending across the North American craton. This graphical representation of the sedimentary sequences of North America shows us 6 unique cratonic sequences bounded by major unconformities. The blue represents marine excursions onto land when sediments were deposited, and the yellow represents exposed land on North America, where unconformities exist. The first cratonic sequence across North America is the Sauk sequence. The rocks of the Sauk sequence were deposited from the late Proterozoic to the early Ordovician and record the first major transgression onto the North American craton. The craton itself was above sea level, and deposition of marine sediments was limited to the shelf areas of the craton. On the map, you can see the exposed land and epeiric seas of the Sauk sequence. This map is the location of the continent during the late Cambrian. We know there were Epiric seas due to the types of rock deposited. In fact, we can delineate where ancient shorelines were located by the clean, well-sorted sandstones, and where the shallow water areas were due to carbonate deposition with the presence of stromatolites and ooids. By the late Cambrian, the Sauk sequence, or the Sauk Sea rather, had covered most of North America. The only areas above sea level were a portion of the Canadian Shield and a few large islands referred to as the Transcontinental Arch that extended from New Mexico to Minnesota and the Lake Superior region. During the Cambrian, North America straddled the equator. This correlates with the explosion of shelly life forms and the deposition of evaporites that we would expect to find in a tropical environment. The craton was not submerged, but the rest of the continent was, with the exception of the transcontinental arch. On the map, you can see where we have sandy deposits, carbonate deposits, and muddy deposits. These are referred to as facies. So for a refresher, what are facies? Facies are time-equivalent units of rock that are deposited laterally adjacent to one another. What that means is that the sands, carbonates, and muds on the previous map were all being deposited at the same time, but at different water depths. In the Cambrian, sandy facies of quartz-rich sand derived from the craton occurred closest to the craton. In other words, they were the shoreline. The craton surface weathered and eroded for 500 million years. There were no land plants yet to help break down rock, so erosion by wind and water was more common. These sandstones are typically well-rounded, well-sorted, 99% quartz sandstones, which are what we would expect to see with this much time for weathering and erosion to take place. This is a facies map showing the location of Cambrian deposition in North America. The blue represents limestone deposition, areas that were underwater. The yellow is sandstone deposition, or shorelines. The light tan is shale deposition. West of the transcontinental arch, we have a classic example of a transgression with limestone in deeper water, shale in the middle, and sandstone in shallow water, all being deposited at the same time. By the end of the Cambrian period, most of North America was underwater due to the Sauk transgression of an Epiric sea that was less than 200 meters deep. This resulted in carbonate-secreting organisms taking over the shallow seaways and depositing great quantities of limestone over the craton. This would have the effect of creating a level topography in some areas. This is the end of part 1. In part 2, we will explore Ordovician global geologic history.